Recall that a function is a rule that associates with each element from a set X only one element in the set Y. So this rule is denoted Y equals f of x. So we can view it as a mapping from a set X to a set Y. So for example, if we have some element in set X, that gets mapped to an element y1. So note that, for example, if we had a parabola, two different values of x can map to the same y value. So effectively, it's a many-to-one mapping. So y is the image of x under f, or f of x is the value of f at x. And x is the domain of f, and y is the codomain of f. So for example, if we had a set X having elements 1, 2, and 3, and set Y has elements 1 to 4, and our rule f of x is equal to x squared. So in this case, the domain of f is the set with elements 1, 2, and 3, and the codomain of f is the set with elements 1 to 4. And the range is the subset of the codomain that consists of all images of points in the domain. So effectively, the range is the actual values that these x values are mapped to according to the rule that's given. So in this case, the range of f is the set with elements 1 and 4. So the square of 1 is 1, the square of 2 is 4, and the square of 3 is 9, which is not inside this set. Now we'll extend functions to vector spaces. So if we have vector spaces v and y, and f is a function with a domain v and codomain of y, then f is a transformation from v to y, or f maps v to y. And if the two vector spaces are identical, then f is also an operator on the vector space v. So if we consider some real valued functions of q variables, so we have some function of x1 to xq, which maps this tuple to y1, and similarly we have y2 is another function of x1 to xq, and so on up to yp, which is some function of x1 to xq. So here we have P equations that assign a unique point or vector having components y1 to yp, which is in a vector space of p tuples, and this unique point or vector gets assigned to each point or vector being x1 to xq that's in the space of q tuples. So we denote this as a transformation from the vector space of q tuples to the vector space of p tuples. So we're going from x to y. And alternatively, we can write this transformation as y1 to yp being equal to t of x1 to xq. Now recall our transformation from the vector space of q tuples to the vector space of p tuples. And now if we have a special case where the equations are linear, so we have y1 is some coefficient of a matrix by x1 plus a12 by x2 and so on up to a1q by xq, and we have a similar expression for y2 being equal to a21 by x1 plus a22 by x2 and so on up to a2q by xq, and we keep going up to p equations. So we have ap1 by x1 plus ap2 by x2 and so on up to apq by xq. So this can be written as the vector y is equal to the matrix A being the matrix of coefficients multiplied by the vector x. So effectively, A is a transformation that maps a column vector in the vector space of q tuples to a column vector y in the space of p tuples. So we can denote this transformation as TA from the vector space of q tuples to the vector space of p tuples. And again, if we have the same number of independent variables as dependent variables, so where p is equal to q, so in addition to being called a transformation from RQ to RP, it's also called the operator. So this transformation can also be expressed as a vector resulting from the transformation of the vector x. Or another notation states that TA maps x to y. So A is called the standard matrix for this transformation. Let's look at several properties of matrix transformations. So for every matrix A, the matrix transformation from the vector space of Q tuples to the vector space of P tuples, where A is the standard matrix for the transformation, then this transformation has several properties for all vectors A and B in the vector space of Q tuples, which we're transforming from, and also for every scalar S. So the first property is the transformation on the zero vector results in a zero vector. So you can look at this transformation as a matrix A multiplied by the zero vector. And we also have two additional properties stating that the transformation is linear. So the first property of linearity is the transformation of the scalar S multiplied by a vector A is the same as the scalar multiplied by the transformation of the vector. And the transformation of a sum of two vectors is equal to the sum of their individual transformations. So the transformation of A plus the transformation of B. So using these linearity properties of a matrix transformation, we see that a matrix transformation maps linear combinations of vectors in RQ. So if we express a vector as some linear combination of other vectors up to R, so this here is a linear combination of a vector in RQ. So transforming this linear combination by the linearity property results in the following linear combination of these vectors. So we have the scalar S1 by the transformation of vector A1 plus S2 by the transformation of vector 2, and so on up to SR by TA of AR. So linear combinations of vectors in RQ get mapped into corresponding linear combinations in RP. And another property that results from linearity is if the transformation from RQ to RP and another transformation with another standard matrix B from RQ to RP, and if the transformation TA of a vector X is equal to TB of the vector X for every vector X in Q space, then the standard matrix for this transformation is equal to the standard matrix for this transformation. Let's look at a method for finding standard matrices for the transformation from Q space to P space. So this transformation, for example, can be a rotation, reflection, orthogonal projection, and so on. So to find a standard matrix for a transformation we first consider the effect of the transformation on the standard basis vectors of RQ. So for example, if we have the transformation of the basis vector E1, that's equal to the transformation matrix multiplied by the basis vector. And similarly, we have a transformation of vector E2 being equal to A by E2, and so on up to the transformation of a vector EQ being equal to A by EQ. So as we know, the standard basis vector E1 has the first component being 1 and the remaining components being all zeros. And E2 has all zeros except for the second component. And so on up to EQ, which has the Q component being non-zero. So remember that we can express the multiplication of a matrix by a vector as a linear combination of the matrix columns with the vector components being the coefficients of the linear combination. So for example, the matrix A by E1 is equal to 1 by column 1 of matrix A plus 0 by column 2 and so on, plus 0 by the final column of the matrix. So as we can see, this is the same as column 1. And if you do the same thing for the matrix A by E2, well, you're going to get a 1 multiplied by column 2. And so on up to the matrix by EQ, which will be equal to the column Q in matrix A. So therefore the transformation matrix A is obtained by augmenting the transformations of the standard basis vectors in each column. So what we have is the transformation of the basis vector E1 augmented with the transformation of E2 and so on, which is finally augmented with the transformation of the standard basis vector EQ. And keeping this transformation matrix in mind, we're going to go through several examples where we develop standard matrices for a linear transformation. Let's develop a standard matrix for the orthogonal projection of some vector with components x and y onto the horizontal axes. And recall our standard matrix for the transformation can be written as the transformation of the basis vectors in each column of the matrix. So here we have 2 dimensions, so we'll stop here. So first, our projection operator applied to the vector with components x and y should result in a vector with components x and 0. And now we'll find the images of the standard basis vectors. So the transformation of the standard basis vector E1 we expect to remain as 1, 0. So remember that E1 is a unit vector with components 1, 0. And the standard basis vector E2 is a basis vector with components 0, 1. So therefore the orthogonal projection of E2 onto the horizontal axes is going to give a point, or a vector with 0 length. So therefore the standard matrix for this transformation is obtained by placing the transformations of each standard basis vector in each column of the transformation matrix. So for the first basis vector we have 1, 0 and 0, 0 for the second basis vector. So therefore, if we apply this transformation matrix to any vector with components x and y, we get 1 by x is x plus 0 by y, and the second component is 0 by x plus 0 by y, which gives us the expected result. Let's derive the operator to do a reflection about the xy plane. So suppose we have a vector with some x coordinate, y coordinate, and z coordinate. So it looks something like this. And to reflect that about the xy plane, we expect the vector to look something like this. So the x and y coordinates remain the same, but the z coordinate gets negated. So therefore the transformation operator on a tuple xyz results in the following tuple. And now we'll apply the transformation to each standard basis vector. So we have E1 which has components 1, 0, 0. So reflecting this vector about the xy plane results in the same vector. And for our next basis vector, being the unit vector E2, which has components of 0, 1, 0, well, this vector is also going to remain the same if we reflect it about the xy plane. And finally, we apply the transformation to the third basis vector, which points in a z direction. So it has components 0, 0, 1. So the image of this vector, if we reflect it about the xy plane, is going to be 0, 0, minus 1. And now we place these images of the basis vectors in each column of our reflection operator about the xz plane. So what we have is 1, 0, 0, 0, 1, 0, and 0, 0, minus 1. And this is our standard matrix for the reflection about the xy plane. So in general, if you multiply this by some vector xyz, we have x by 1 plus 0 by y plus 0 by z, and then 0 by x plus 1 by y plus 0 by z, then 0 by x plus 0 by y plus negative 1 by z, which is our reflected vector as expected. Suppose we want to rotate a point or vector through some angle theta about the axis pointing out of the plane. So again, we look at what the transformation is going to do to our standard basis vectors, being E1 and E2. So E1 would be rotated by the angle theta, and similarly for E2. So these vectors will be rotated anti-clockwise by some angle theta. So applying our transformation to E1, which had initial components of 1, 0, well, the transformed vector is going to have a horizontal component of cosine theta and a vertical component of sine theta. So note that these basis vectors are unit vectors. So when we rotate them, they still have a length of 1. And applying the transformation to the second unit vector, our second unit vector had initial components of 0, 1. So its new components are minus sine theta, which is this component over here, and the vertical component is cosine theta. So these are the images of the standard basis vectors. So therefore our standard matrix is cosine theta, sine theta in the first column, and minus sine theta, cosine theta in the second column, which is our standard matrix for a counterclockwise rotation through the angle theta. Now let's multiply this standard matrix by some vector with x and y components. So we'll take the image of this vector as having components xt and yt. So if we multiply this matrix by this vector, we get x cosine theta minus y sine theta and x sine theta plus y cosine theta. So these are called the rotation equations for R2. So these equations are for a counterclockwise rotation. But if we wanted to rotate a vector clockwise by the same angle, then you just replace theta with minus theta. Let's derive the standard matrix for shear in the x direction. So if we have our standard basis vectors, and visualize these as forming a square, well, a shear transformation in the x direction is going to distort this square so it becomes a parallelogram. So our vector E2 ends up here, and the basis vector E1 remains unaffected. So applying the transformation on each basis vector, we have the transformation applied on E1, which results in an image of 1, 0. So this vector remains unaffected. and then applying the transformation on E2, which has initial components of 0, 1, while the component of this vector in the horizontal direction is our shear factor, and the vertical component remains the same. So therefore our standard matrix for this transformation is 1, 0 and S1. So note that if S is less than 1, then our shear distortion will be in the opposite direction.